So I want to start off this second video for part one of the class by making just a bit of an apology. And that is, this is still part one of the class, but I want to present kind of an overview and a summary of the things that are going to be measured regarding part two of the learning objectives, which are measured and presented within part one of the class. And I apologize just for the confusion. When I started designing this class, the class itself fell into some specific sort of conceptual parts, 5 conceptual parts, which made sense to me. The learning objectives, however, kind of were grouped conceptually into what ended up being more than 5 parts. And rather than use another word for those groupings, I, for some reason, use the word part for them too, and that's just very confusing. So part one of the class focuses on parts 1 and 2 of the learning objectives. And I know that's confusing, but that's just the way it is. And I apologize, and I'm just saying it now. The first video presented during week 1 regarding the course notes and the content addressed all those learning objectives that were part of part 1 of the learning objectives. And this video, I want to provide just a little bit of background and storytelling to help you better understand the overall concepts that are covered by the learning objectives that begin with the number 2, or are part 2 of the learning objectives. So here we go with that. So one of the first categories of learning outcomes that I have for part 2 of the learning objectives are science and education. So I have learning objectives related to what the scientific method is, or not what the scientific method is, but what a scientific method is. And then there is an emphasis on theories of learning. And that is a direct sort of response to the presentation of an understanding of what a theory is and how important theories are in education, in research, and in professional practice. And I'll give you a good example of that personally, and it's something I'll talk about later in when I'm talking about the learning objectives for this part of the class. And that is, as a science educator, I acknowledged early on in my profession that one of my roles would be to help my students become better scientific reasoners. And one thing I learned about scientific reasoning, which is a construct, and that's something that you're going to be learning more about in this part of the class, what a construct is. Scientific reasoning, one thing I learned is that students don't naturally mature into becoming scientific reasoners. In fact, research suggests very strongly that adults don't naturally mature into becoming scientific reasoners. It needs to be taught. And as a science educator, it became really important for me to focus my instructional efforts on helping to facilitate skills associated with scientific reasoning. Now, those skills were grounded in a theoretical model of development and learning, and the model was defined by an educator named Jean Piaget. And Piaget developed a model of cognitive development that sort of described the reasoning abilities of humans from the time they're born through adulthood, and by defining what cognitive development was and what reasoning skills were, Piaget laid the foundation for helping to operationalize scientific reasoning, or, if you will, critical thinking skills, And being able to operationalize it meant that that educators were able to better understand what it means to possess those skills. What does it mean to have scientific reasoning skills? And so one of the things that I was lucky enough to be a part of when I was a graduate student at Arizona State University, I started out as a grad student studying biology, just biology. But I was so lucky to have a professor. He was a zoologist, but his area of research and interest was in science education, and more specifically, how science educators could design learning experiences that could cultivate the learning of scientific reasoning skills. And so using theoretical approaches to cognitive development, Piaget approaches, this professor was able to create some measurement devices that communicated scientific reasoning. And I'll show you an example of that a little bit later in this presentation. But I wanted to bring this up because the first part of these objectives has to do with learning about some fundamental features of the scientific method, and then also learning about what makes a good theory and what are some foundational educational theories that help define educational practice in many different ways. The learning objectives progress to using the scientific method as a way of knowing compared to other ways of knowing, which was part of the very first part of the learning objectives, and research as a scientific method, as a way of knowing. And so the learning objectives in this category focus on things related to the difference between deductive and inductive approaches to research and also science. And that was really important to me because one of the things I learned as a science educator is that I could develop inquiry-based experiences that were either deductive or inductive ways of helping my students sort of solve observable problems in science. And so you're going to learn a little bit more about deductive versus inductive research and reasoning. Then the learning objectives move into general research fundamentals, which focus mostly on variables and types of variables. And that's so important. And so being able to understand the different types of variables, what an independent variable is, what a dependent variable is, what a moderator variable is, those are all really important fundamental things to understand as you learn more about science and how research is a way of using science to ultimately know things, right? Then the notes and the objectives focus on sampling, and one of the things that I want to say about sampling is that whenever you read a research study in education, or anything else for that matter involving human subjects, sampling is one of the most important elements to the design of research that could have a really important impact on number one, how valid and reliable the results are of the study, but number two, what claims can be made about the results of a study. And I'll give you a really good example of sampling that's come up over the years in the field of education. You might be familiar with a test that is carried out, or I should say a study that's carried out about every 3 years. and it's an international study. It's called the Program for International Student Assessment, or PISA. And whenever you hear statements like, "Oh, the U.S. ranks, 12th in the world in reading ability, or scientific reasoning, or math skills," usually people are referencing this global kind of research-based study that's implemented. And again, it's called PISA, or the Program for International Student Assessment. And there has been some ongoing controversy since the early 2000s about the results of the studies based on sampling. And I'll tell you what that is in general, what the controversy is. And it goes like this. So the assessments that are used to measure the skills associated with the PISA test, and these are application skills in the real world, math skills, reading skills, reasoning skills, the results are always communicated and ranked by the students in different countries that participate in the study. And it's a lot of the most organized and advanced countries in the world that participate in this. And so the U.S. is their data are provided, and we always tend to fall somewhere in the middle when you rank countries by math skills at age 15. And reading proficiency at age 15, and some of the other skills that are measured. However, the controversy about the results are focused on how are the 15-year-olds sampled from each country. And I say that because one of the countries that consistently ranks as one of the most successful or highest levels of math and reading are some Asian countries, particularly Shanghai, which is a region in China that is isolated as a population that contributes their data to this study. And one of the things that is interesting about the sampling for the 15-year-olds from Shanghai is that by the time you're a 15-year-old in school in Shanghai, there are a lot of filters in place regarding who moves through the education system in China by the time they get to 15. And for example, there is a subpopulation of people in China that are kind of equivalent to migrant workers in America, lower socioeconomic status and not a stable living condition. Well, there are no students from that subpopulation are sampled from the 15-year-olds who take the assessments in Shanghai. But but in the United States of America, the 15-year-olds are sampled from, it's a relatively random sample from any 15-year-old in school in the United States. And that certainly includes members of the population who are much lower SES, as well as members of the population who are living in very transient homes. And one of the things we learned about doing research on factors that affect success in school in America, and again, these are all correlational, but one of the factors we learned is that there is a well-established, strong, and consistent correlation between a learner's socioeconomic status, their SES, and their achievement in school, and their success in high school, as well as their whether or not they go to university or college after high school. That is a very well-established, significant relationship. That doesn't mean that poverty causes poor performance in school. It means that there's a relationship between people of lower means in America and their success in school. Of course, when you want to try to investigate the variables that that might actually cause lower success in school, it might have as much to do with nutrition, right? Like who's getting better nutrition, who's not working outside the home, you know, what's the stability of the home environment? How many parents or tutors are enlisted to help students who might be struggling? So those are factors that are also related to socioeconomic status that may in fact have a profound impact on success in school. But it's not because you're poor, it's because there are other factors related to being poor that actually lead to poor performance in school. And so certainly the same thing could be happening with if you remove those students from the lower transient and lower socioeconomic status from the population, then that's going to skew your results. So that's why sampling is very important if you want to generalize the results of your study to, to anything else. And so sampling is a very important thing you're going to be learning more about in part 2 of the class. Then it moves to the objectives on measurement and how you measure certain things. And there are different types of data that you're going to learn more about in the notes regarding types of data and what you measure. And you're going to learn about nominal, ordinal, interval, and ratio data a little bit from the notes. And then also, how do you measure certain important concepts and constructs, and what do those data look like? And so you're probably very familiar with Likert or Likert type scale survey data, where participants are asked to register their level of agreement with certain statements, and the process of developing those kinds of measurements is really important, and it's something you need to learn a little bit more about, and something that, again, is presented in the notes now for part 2, but also applied later in the course. Then you're going to look at a little bit about types of measurement, validity, and reliability, and that's just the important factors related to whether or not when you measure something in education, the measure actually measures what you want it to measure. So in the case of scientific reasoning, are items on a scientific reasoning test, do they actually measure what you want them to? And here I'm going to show you an example right now of a measurement of an item on an assessment that might measure scientific reasoning. So I'll show you that now. And finally, there are some learning objectives related to data analysis and statistics. And these are just basic concepts, many of which I'm sure you've heard before, like descriptive statistics that communicate averages or means, and range and mode, those kinds of things. But the information in the course notes sort of divides or categorizes data based on kind of the level of variables being communicated. One area is univariate statistics, and that would be one variable. And so if you're communicating about data you collect on one variable, one very, very common assumption that are made by researchers who, again, are collecting data from humans is that humans tend to, all variables tend to fall within a very predictable kind of distribution or frequency distribution regarding the level of measurement for different things. And you probably have heard or seen this before, the normal distribution. Here's a graph of that. What this graph shows is not only that if you take any variable related to human beings, and it could be a score on a math test, it could be IQ, could be height, foot size, it could be however you want to measure something like sexual orientation, for example. All responses to items that measure individual variables among humans tends to be distributed in a shape, in a way that when it's communicated in a graph, it looks like a curve, like this bell, like a bell-shaped curve. And when you look at the distribution of the number of people who fall within a certain level of variation, there's a descriptive measurement for level of variation called standard deviation. And that number reflects the average distance that somebody's value resides relative to what the average of everybody in a sample is. And what this normal distribution shows you is that you can, again, for any variable you're thinking about, approximately 68 to 69% of your entire sample will fall within one standard deviation from the average of the sample. That's a fascinating consistency in human beings, by the way. And a lot of the analytics that you apply to data you collect when you're studying humans, a lot of those, the math involved make the assumption that this is the way the data from a sample should look. Okay, so if it doesn't look that way when you collect data, then you know something interesting is going on. And so normal distributions are related to univariate statistics. There's also bivariate descriptive statistics where you're looking at the relationship between variables, and that's where something like correlations come into play, where you're correlating, again, when the value of one variable in a sample of a population, what's the relationship between how that variable changes and how another variable might change. And so that's bivariate. And then there's inferential statistics where you're trying to mathematically sort of examine the probability that something that you don't know might be the reality based on things that you do know. And it's rooted in fundamental trigonometry, to be honest with you. If you look at the model equations for what drives inferential statistics, any of you who have had trigonometry, you know. So if you know two values, you can accurately predict what the value of the third should be, whether it's an angle or or the length of a side. So that's inferential statistics. So those are some of the fundamental ideas that are presented in the notes for part 2. Read through them, and if you have any questions about them, again, since we're not using a text, it's important that you evaluate the notes and then communicate with me if there's something about it you don't understand, or go online and do some searching. You can use AI, or you can look at other research texts or other, social science texts that might help clarify things. But I'm happy to help if there are things you don't understand. Now, this covers all of the objectives that are presented in this class for the part 1 that's going to be measured by exam number 1. So once you review the notes for objectives that begin with the number 1 and begin with the number 2 that are not italicized, you can take the practice exam and see how well you do. And again, if you have any questions about things that you were not successful in that practice, let me know. Or if you have questions about it, and I'll be happy to help clarify things for you. So good luck with that.